Okay, in section 4 we're going to start talking about exponential and logarithm equations and how we solve those equations. So we're going to start out with this word problem. So take a minute, maybe pause the video, read the word problem, and then we'll go on from there. Okay, so we've got our exponential equation where they tell us in the problem that the value of r is going to be 17. So we end up with this equation, 17 is equal to 6 times e raised to the 12.77x. So we have what's called an exponential equation because we've got an equation that has an exponential within the equation. So how are we going to solve that? We don't really have any tools for solving that yet. So we've got these rules here for solving exponential equations. First step is always going to be to isolate the exponential. Get the exponential piece all by itself. Once we've done that, to undo an exponential, remember that exponentials and logarithms are inverse operations. So if I've got an exponential, I'm going to use a log to undo that. And once I've taken the logarithm of both sides, then I'll be able to solve for the x. So that's what we're going to do with this equation. Okay? So here's our equation. So the first thing we need to do is we need to get the exponential piece by itself. So we're going to divide both sides by 6. And I'm just going to leave that as 17/6. There's nothing I can really do to it. Okay? So now what I'm going to do is I'm going to take the log of both sides. So since this exponential has a base of e, what I'm going to do now is I'm going to take the natural log of both sides. So if I take the natural log of both sides of this equation, the natural log of e to some power, remember those rules that we had way back in the beginning, those properties of logs and exponents, is going to just leave me with the 12/7700ths x. Because the base of the log and the base of the power match, the exponent is all I'm left with. And on the left side, I have this natural log of 17/6. So now all I have to do is isolate the x. So to get x, I'm going to take the natural log of 17/6, and I'm going to divide whatever that value is by the 12/7700ths. Okay? So when we do that, we'll be able to get our value of x. And x is approximately 0.08, which is the legal limit for blood alcohol and your DUI type situations. Okay? So you notice that when we have an exponential in the equation, we're going to use a logarithm to get rid of that exponential and give us something that we can plug into our calculator. Okay? Here's another property that we need to be familiar with. If I have two powers that are equal, and they have the same base. Notice that both of these things are base b. If the bases are equal, then that tells me that those exponents have to be the same. So if I have a base to the m and the same base raised to the n, then I know those two exponents have to be equal. So the way we use that in an exponential equation, we can see here in this example. I've got 2 raised to the 3x minus 8 equals 16. Well, I can rewrite 16 as a power with a base of 2. So now I've got a base of 2 on the left, I have a base of 2 on the right. If the bases are the same, then that implies that our exponents have to be equal. So the 3x minus 8 equals 4, and that allows me to solve for x. So if I have an exponential, one of the methods we can use is if I can write both sides of the equation as powers with the same base, then I can just set the exponents equal and I can solve from there. Okay. So let's look at this example. We've got 27 raised to the x plus 3 equals 9 to the x minus 1. Well, at first glance, it doesn't appear that they have the same base, but we can change them so that they do. I can write 27 as 3 to the third power. Okay? And that's still being raised to the x plus 3. I can write 9 as 3 squared, and that's still being raised to the x minus 1. So what this really is this is 3 raised to the 3 times x plus 3, because when I raise a power to a power, I multiply the exponents. This is really 3 raised to the 2 times x minus 1. So now I have two exponential expressions, two powers that are equal, and they have the same base, which means that their exponents have to be equal to each other. Okay? So that would give me 3x plus 9, 2x minus 2, which means I'm going to end up with x equal to what? Subtract x, subtract 9, negative 11. Okay? So by taking those powers, those exponential expressions, and writing them in terms of the same base, I'm able to set the exponents equal to each other and solve. Okay? Now, in the next example here, we have an exponential equation, but can I write 4 and 15 both as powers of the same base? And the answer there is no. So what we're going to do is, in order to undo that exponential, we're going to take the natural log of both sides. So if I take the natural log of 4 to the x, that would be equal to the natural log of 15. Okay? As long as I'm doing the same thing on both sides, it's okay, as long as I take the natural log on both sides. So now we're going to use our properties of logarithms. The natural log of 4 to the x is really the same thing as x times the natural log of 4. So now I can get the x by itself. And x would be the natural log of 15 divided by the natural log of 4. And now that's something I can just plug into the calculator and come up with a solution for. So if we wanted an exact answer, we would just leave that. If we want the approximation, we could put that into the calculator and see that that's approximately 1 and 95/100ths. Okay? Which kind of makes sense, because if it were 2, 4 squared would be 16, so it's got to be relatively close to 2, because 15 is pretty close to 16. Okay? So let's try another one. We've got an exponential, because I can see e raised to the 6/10 x. So our first objective is going to be get that exponential by itself. So the first thing would be to get rid of the minus 3. So that would give me 240. Now I want to get e to the 6/10 x all by itself, so I'm going to divide both sides by 40. And 240 divided by 40 would be, oops, not 60, that's too many zeros. Would just be 6. Okay. And now I've got an exponential with a base e, which means I'm going to take the natural log on both sides. Okay. So if I take the natural log on both sides here, the natural log of e to a power would just leave me with that exponent. Okay. So now x would be the natural log of 6 divided by that 6/10, which means x is approximately 2.99. Okay? So again, isolate the exponential. Okay? Get the exponential piece all by itself. That's the first step. Second step is, once we've done that, we're going to take the log of both sides. By taking the log of both sides, we're able to get the x term and get the x term isolated. Okay? So this looks a little bit different. E to the 2x minus 4e to the x plus 3 equals 0. So it's an exponential equation, but it actually has some similarities to some other things that we've done. Okay? Let's suppose I were to do this. Let's say I said let u equal e to the x. Okay? If I do that, then I could rewrite this, and it becomes u squared minus 4u plus 3 equals 0. And that should look familiar. That's just a quadratic equation. Okay? This is what we call a u substitution. You use this in calculus often when you're doing integrals. Okay? So this is something we're familiar with. We could factor this. So u minus 3 times u minus 1 equals 0. And now that I factored it, I go back and I replace the u with the e to the x. So that's e to the x minus 3 times e to the x minus 1 equals 0. Well, when I factor something and it's equal to 0, it means that one of those factors has to be 0. So here I have e to the x equals 3, here I have e to the x equals 1, and I have an exponential equation with the base of e, which means I will take the natural log on both sides. So what do I end up with? I end up with x equals the natural log of 3. And over here I'm going to have x equals the natural log of 1. But what is the natural log of 1? That is just 0. Okay? So by using this u substitution, we're able to take that equation that's an exponential, even though it's similar to a quadratic, we can change it to look just like a quadratic, get the factors, and then put the exponential piece back in and solve the equation from there. So let's shift from exponential equations to log equations. So I have a log base 4 of x plus 3 equals 2. Okay? If you remember, we had a property way back when that said if I had b raised to the log base b of x, then that would simplify to just x, whatever I was taking the log of. So we're going to do the same type of thing here. We're going to take these logs and we're going to undo them, thinking of them as exponentials. So what I'm going to do is I'm going to write both of these things as exponents with the same base. And the base needs to match whatever the base is of the log. So I'm going to rewrite this as 4 to the log base 4 of x plus 3 equals 4 raised to the second power. And when I do that, I can apply this earlier property to this left side. 4 raised to the log base 4 of x plus 3, that's simply going to leave me with x plus 3. 4 squared, well, that's just 16. So I solve for x, and I get x equals 13. Okay? Now another way to think about this is really kind of like just using the definition of logs. Okay? If you remember the definition of logs, we said it means 4 raised to this power is going to equal whatever was in the log. And that's really what we have. 4 raised to the second power, that's right here, equals the x plus 3. Well, 4 raised to the second power was the 16. And what was I taking the log of? I was taking the log of x plus 3. So I know that x plus 3 has to be 16. So really that's how I usually think of it. But it's really this property here that generates the ability to do all that. Okay? So let's look at the next example in the green here. I have 3 natural log of 2x equals 12. So just like with exponentials, in order to solve the logs, we want to get the log by itself. So the first thing to do here would be to divide by 3. So I'd have natural log of 2x is equal to 4. Okay? Well, what is the base of the natural log? Remember, the base of the natural log is really just e. So if I were to take and make both of these things the exponents with the base of e, and then what that does for me is it tells me that 2x is equal to e to the 4th power, which means x is e to the 4th divided by 2. And we would just leave that unless it asked for an approximation, in which case we would type it through the calculator. But if it just said an exact answer, then this would be an exact value. Okay? So if it says approximate, put it through the calculator. If it doesn't say anything about rounding or approximating, just leave e as a power. Okay? So take a second, stop the video, and see if you can do this problem on a sheet of paper, and then come back and compare it to what I do here. So we're going to solve this. So if we use our properties, I know that the x plus 20 has to be equal to 2 to the 3rd power, which means that x plus 20, 2 times 2 is 4, times another 2 is 8. So x has to be negative 12. Okay, pretty straightforward, pretty simple. Notice here's my 2. I raised it to the 3rd power, and it's going to be equal to whatever I was taking the log of. Okay. Now, do the same thing. Pause the video, write this one down and see if you can solve this one. So remember what I said, in order to solve a log equation, you have to isolate the log, which means I can only have one log statement. So here's where that condensing stuff comes back into play. If I'm adding two logs, I can combine those things using our product rule. So this is really the log base 2 of x times x minus 7 equals 3. Now that I have it as one log statement, I can really think of it as taking 2 and raising it to both of those powers, which would give me the x times x minus 7 equals 2 to the third power, which is 8. So now I just have an equation. I'm back to doing algebra again. So I'm going to distribute x squared minus 7x. I'm going to move the 8 over because I have to set equal to 0 to solve. So now I can factor minus 8 and plus 1. So I have x equals 8, and this would give me x equals negative 1. Okay. Now one thing we have to make sure we do is we have to make sure we check our solutions. Are they valid? Are they going to work? Well, this is the one that causes me some concern, because if I have negative 1 and I go back up here and I plug it into here or here, either one, in either case I have the log of a negative number. Remember, I cannot take the log of a negative. The domain of the log function is only 0 to infinity, which means this one is what we call an extraneous solution. It's a solution that we come up with, but it does not work. So the only valid solution here is going to be the 8. Okay, almost done. Okay, so take a second and see if you can solve this problem using the properties of logarithms and solving the log equations. Alright, so first thing we talked about is we need to isolate the logarithms, which means I need to try to combine those two. Well, it's a subtraction. We can do subtraction, that's just a quotient rule. So x plus 2 divided by 4x plus 3 equals natural log of 1 over x. Okay? So now I have two natural logs that are equal. If I have two logs that are equal, then whatever it is that I happen to be taking the logs of, those things have to be equal. Okay. So I just need to set the x plus 2 divided by 4x plus 3 equal to the 1 divided by x. And now I have a proportion. So how do I solve a proportion? Yes, we are going to cross multiply. That would be the easiest thing. Okay, so that's going to give me x squared plus 2x is going to equal to 4x plus 3. It's a quadratic, so there's an x squared, so I got to get everything equal to 0. So x squared, that's going to be minus 2x when I subtract the 4, and a minus 3 equals 0. I believe this will factor x minus 3 and x plus 1, which means I'm going to end up with 3 and negative 1. So again, I have to go back and check and see, are there any situations where either of those values are going to cause me to get something invalid? Well, if I put in 3 plus 2, that's positive. 4 times 3 plus 3, that's positive. So 3 is okay. Okay. If I put in negative 1, okay, if I put in negative 1, then I'm going to end up with negative 4 plus 3, which is a negative 1. I cannot take the natural log of negative 1. So once again, this value here has to be dropped. And the only valid solution is going to be the x equals 3. Okay. Alright, so here's another application problem. I want you to take a second, read the problem, and see if you can solve it. Okay, so let's see what we've got. So percentage of adult height attained by a boy who is x years old, so x is going to represent our age, is given by this log function. Okay, so x is the boy's age between 5 and 15, so there's our domain. And f of x is the percentage of the adult height. So at what age, okay, which means I'm looking for x, has the boy attained 85% of his adult height? So what is the 85% going to be? Well, that's going to be our f of x. Okay, it says f of x represents the percentage of the adult height. So we're going to put, in place of f of x, we're going to put in the 85. We'll have 29 plus 48 and 8/10 times the log of x plus 1. Okay? So from here, we're just going to need to solve. So we're going to take 85, we're going to subtract the 29. So 85 minus 30 would be 55, so that's going to be 56 equals 48.8 log of x plus 1. And then we need to get log by itself, so we'll have 56 divided by 48 and 8/10 equals the log of x plus 1. Well, what is the base of this log? The base of this log is 10. So when I get rid of the log, I'm really going to have 10 raised to the power of 56 divided by 48 and 8/10. That's going to be our exponent, equals x plus 1. So once I evaluate 10 to that power, and then I would subtract the 1, we should find that x is going to be about 14. So what we're saying here is that by the time a boy is 14 years old, at age 14, he's reached 85% of his adult height. So he's going to grow a little bit more, but probably not a whole lot. Okay? All right, so tomorrow class, we'll see if we got any questions that we can clear up, and we'll work on solving some exponential and some log equations. We'll see you then.